Hi, and welcome to this talk on the UNLP 2024 shared task on fine-tuning large language models for the Ukrainian language. This is a joint work done by Oleksiy Syvokon, Mariana Romanyshyn, and Roman Kyslyi. The participants of the shared task were required to fine-tune a large language model, or LLM, to perform two primary functions. First, answering questions about the Ukrainian language, history, and culture, and second, generating text in fluent and accurate Ukrainian. Correspondingly, we introduced two evaluation tracks, each having its own dataset and metric, multiple choice exam questions, and open questions. We will talk about them in a bit. We wanted the final models to be useful for the end user, solutions to be reproducible, and competition to be fair. To reflect this, we established a set of rules. The base models must be open weights. Examples of such models include Mistral, Llama, Gemma, and so on. Participants were free to use whatever compute and data they need for training. However, for inference, we limited models to just one GPU with 16 GB of VRAM. Participants could rely on having a GPU with CUDA compute capacity of at least 8.6, and this includes some higher-end desktop GPUs such as NVIDIA RTX 3090, because we wanted these models to run locally on high-end desktop PCs. CPU memory and disk offloading were not allowed. Resultant weights must be published openly. We also allowed advanced techniques such as retrieval augmented generation, complex prompting, and decoding techniques like speculative decoding, for example. Now we will discuss two datasets and evaluation metrics corresponding to two parts of the model evaluation, exam questions and open questions. We will start with the exam questions. This dataset enabled us to evaluate the model's ability to handle structured, factual information related to Ukrainian language, culture, and history. As a source for exam questions, we used the Ukrainian External Independent Evaluation from year 2006 to 2023. We selected two subjects, Ukrainian language and literature and history of Ukraine. We performed minimal post-processing, which included extracting questions with only one correct answer and removing questions with images. We preserved the basic formatting but reformatted it as a markdown, as formatting is meaningful in many cases. Here you can see an example of one task. So we have a question text and we have a number of destructors and one correct answer. So the model needs to answer with a single letter corresponding to the correct answer. We split the dataset into train and test partitions based on the exam years. So years 2006 to 2019 go to train, which makes slightly over 3,000 examples, and the rest goes to test with about 700 examples. Next, we will discuss the open questions dataset. So it consists of a number of instruction prompts for text generation tasks. Each prompt is related to one of the following categories. And categories are like composition tasks, for example, write text on a given topic, rewrite tasks, for example, simplify text, add humor, add emotions, and so on, evaluation task, for example, analyze emotions in the text, and some common knowledge questions related to the Ukrainian culture. This dataset was crafted specifically for the shared task by two native speakers of Ukrainian. Here you can see some examples. To the left is the original Ukrainian, to the right is a translation to English. Examples include things like tell me the plot of the fairy tale The Cat and the Rooster, is Dnipro a river or a city, or here is a text and then goes a long excerpt, and then the question how many hunters were there in the text. The open question dataset was split into a development set of 20 questions and a test set of 100 questions. This may not seem like a lot, but in fact it's in line with similar benchmarks and is enough to get a good estimate of model utility. We employ human judgments to compare models. We run head-to-head evaluations. Here is an example of the UI that we provided. You can see that it consists of a task, An annotator would see the task and the two different models' outputs generated for this task. The annotator doesn't know which models are behind these answers. The annotator has to vote either for model 1 or model 2 or decide that it's a tie. We provided some evaluation guidelines. For example, the answer must be in Ukrainian, the answer has to follow the instructions, it has to be factually correct, grammatical and stylistically correct, and also, which is quite important, it should reflect your subjective preference. Now let's talk a little bit about the evaluation metric we use for this task. We employ a metric called TrueSkill. TrueSkill is a rating system developed by Microsoft Research. It's used in Xbox Live for ranking players, and it quantifies players' skill using a Bayesian inference algorithm. Every skill is defined by two parameters, mu, which is the average skill of a player, and sigma, which reflects the uncertainty of the rating. A player's real skill is estimated to be within 2 sigmas with 95% confidence. To get some intuition about how this metric works, let's go through a toy example. Imagine we have 3 models competing in an evaluation. They all start with a mean skill of 25 and a sigma of 8.33. There are no votes when we start. Now, say in the first round of evaluation, we present users with the output of model A and model B, which were randomly chosen. If the human picks model A, this results in the skill rating of model A increasing and the skill rating of model B decreasing. Also, the sigma, which you can loosely think of as an uncertainty of the rating, decreases because we now have some evidence and every model have a single vote. Now, let's say that the outcome of round 2 is that the model C beats model A. This results in model C getting a much higher rating because it just has beaten a stronger model, and the rating of model A drops. The confidence, or should I say uncertainty, of both models decreases. And now the model A gets 2 votes and other models has 1 vote. As we run more and more rounds like this, our confidence in the ratings increases and the average skill hopefully converges around the real values. Now let's move on to the actual results. We have 22 teams registered for the task. We got 4 final solutions qualified as valid ones. We have 2 published papers so far. For the exam questions, the team named Sherlock achieved the highest accuracy of 49% using retrieval augmented generation. Without RAG, their accuracy was 42%. You can find implementation details of these models in their corresponding papers published in UNLP 2024. In the open questions track, Sherlock again led the pack with a true skill mu of 26.77 without RAG and 26.27 with retrieval augmented generation. You can see that we have more than 300 votes for every model, and this is enough to reduce uncertainty to the reducible Bayesian error, which means that more votes wouldn't help. So we were also curious to see how the submitted models stack up against the proprietary models. So we've conducted some human evaluations against GPT-4 version 0613, and the results are presented here. You can see that GPT-4 has an estimated skill of 28.48, whereas the next best model has a skill of 25.05. Of course, GPT-4 is a much larger model, so it's not compliant with our rules, but clearly there is a gap to be addressed in the future. I would like to close this talk with acknowledgements. We thank Natalia Romanyshyn for her contribution to the open questions set. We also thank 63 members of the Ukrainian NLP community for assessing the models. You're all awesome. The Codabench page has all the starting kits, all the data, evaluation scripts, and it's still active. You're welcome to submit your solutions here. It will stay open. Additionally, you can find all the data and scripts on the GitHub page. Thank you.